This screencast is about square root functions and inequalities. And we're going to be able to graph and analyze these functions and inequalities so that we can use them. So we're introducing a new family of functions called the square root family. So the parent function of the square root family is f of x is the square root of x. And this is what the graph of that looks like. It starts at the origin, and because we can only take the square root of positive numbers in the real number system, the domain is only the positive values of x. So it's only everything to the right of the y-axis. The range is also going to be positive numbers. The square root of x itself is a quadrant 1 function. Starts at the origin, then heads into quadrant 1, always increasing. Intercepts occur at the origin only, x and y intercept. This function is not defined for negative x's in the real number system. And as x increases, the function is increasing towards positive infinity. So to transform a square root function from that parent function, the square root of x, there's the square root of x. All of these transformations work exactly like they do for the other types of functions, mostly polynomial functions that we've looked at so far. So if I have a function that's in the form f of x equals a times the square root of x minus h, quantity, plus k, that point h comma k is kind of like a vertex. It's a very important point. For the parent function, that's 0, 0. If I need to move the graph to the right, I'm going to change the value of h such that x minus h equals 0. So if I want to move it to the right, I'm going to make that h value positive. I'll have x minus a positive number. And if I want to move it to the left, I'm going to make it x minus a negative number, which is x plus. Okay, so if h is positive, it translates to the right. If it's negative, it translates to the left. Just like with other functions, the k term will translate up and down. So if I want to translate it up, I add a k. If I want to translate it down, I subtract a k. If the a value in front of it is positive, then it's going to be an increasing square root function, like the parent. If the a is negative, it's going to be reflected across the x-axis. The square root of negative x would look exactly like the square root of x, except that it would be reflected across the x-axis. The final transformation, if the value of a is between 0 and 1, not including those points, then the graph is going to be compressed vertically. If the value of a is greater than 1, then the graph is going to be stretched vertically. Okay, what that means is for a's greater than 1, it's going to increase faster. For a's less than 1, it's going to increase more slowly, decreasing in the case of negative a. Now, that h comma k, it's not a vertex, but it represents either a minimum for an a greater than 0 function or a maximum for an a less than 0 function. Because for a minimum, it's always increasing past that point. For a maximum, it's always decreasing past that point. Let's go ahead and look at graphing and analyzing an equation that involves a square root. So we got y equals 3 times the square root of x minus 4 plus 2. So we'll set up our coordinate system. We know the minimum is at h comma k is 4 comma 2. So we're going to go to 4, 2, 1, 2, 3, 4. And we know it's a minimum because this a term is positive. 4, 2. That's going to be our critical point that the square root function begins at. We're going to make a table of values from x equals 4 on up because x cannot be less than 4. X minus 4 has to be greater than 0. So all the x's greater than or equal to 4 are in our domain. So we're going to make a table. 4, 5, 6, 7, 8 are some good points to pick. At 4, it's 4, 2, 5, 5, 6, 6.2, 7, 7.2, and 8, 8. So when we plot those points, 5, 6, 6.2, and 7, 7.2, we know that's stretched 3 times from the original function, the parent function, because the a term has a 3 on it. It's positive 3. So we notice the original square root function looks something like this, the parent function. We can see that this function is stretched out significantly more. We also know the graph, we've already translated it across to the right 4 and up 2 because of the 4 comma 2 and the h comma k. And that leads to our domain being all x's greater than or equal to 4. And our range is all the y's greater than or equal to -2. Everything above 2 on the y side and everything to the right of 4 on the. Let's take a look at another one. Another example. Graph and analyze the function y equals negative square root of x plus 5 quantity minus 6. Well, we know that the h is going to be -5 and the k is going to be -6 because -5 is what makes this x minus -5. So h is -5, k is -6. We'll make a table of values going from -5 to the right because we've got to have positive numbers in this radical symbol. We know that the graph is going to be horizontally flipped from the parent function square root of x because the a term is negative. So instead of increasing, it's going to be decreasing. And we know the graph is going to be translated 5 left and 6 down from the parent function. So we make our table, -5, -6, -4, -7, and so on. We plot our points. The critical point is this one right here. This graph is a little bit misleading. Every x square is -2.5 and every y square is -2. But this is -5, -6, -4, -7, and so on. But this graph is translated 5 left for the h -5 and 6 down because the k is -6. And instead of increasing, it is decreasing. Its domain is going to be all all values of x greater than or equal to -5. Its range is going to be all values of y less than or equal to -6. Let's look at an inequality. Okay, so we're going to graph the inequality y greater than square root of 3x plus 5. Like with any inequality, we're going to graph the boundary equation. In this case, y equals square root of 3x plus 5. Now, we've got to do a little bit of work here. We got to find the h value. The k is 0 because there's no number after the radical. But we got to set 3x plus 5 equal to 0 to find our h value. And when we do that, x is going to be -5/3. Once we move the -5 to the other side, and then we divide by 3. So our h value is -5/3. So since h is -5/3, we're going to go ahead and k is 0. That means our vertex is at -5/3, 0. So our h, k, our vertex is at -5/3, 0. Now it is not part of the solution because this is a greater than. So we're going to have an open circle instead of a closed circle. And then when we graph it, using the principles we talked about before, it's just like the parent function. Actually, it's positive a +1 for a. So it's really just shifted to the left by 5/3. There is no vertical shift. There is no stretching or shrinking. There is no flipping. So it is just like the parent function translated to the left by 5/3. So now, as with any inequality, we're going to test a point to see if it's part of the solution. It can't be a point on the boundary line. My personal favorite for inequalities, if you can, is 0, 0. Well, if we test 0, 0, and we put in a 0 into the inequality, we get 0 greater than the square root of 0 plus 5. Well, 0 is not greater than the square root of 5. What that means is, instead of shading this lower region, I'm going to shade the upper region. So we'll shade the region that does not include the test point. Now notice, this region starts at -5/3 for x and goes to the right. It does not include anything to the left of it or below the boundary. And so the blue area is the solution to the inequality y greater than the square root of 3x plus 5. But as far as it goes, the inequalities, the translations, they all work just like they do with polynomials and other functions that we've looked at. So we've looked at square root functions and inequalities and how to graph and analyze them so that we can use them in practical situations.